Okay, so we are going to talk about some classes of regular semigroups. Well, we know already that a semigroup, just let us first start with a definition of semigroup. A semigroup is a non-empty set. S together with an associated binary operation. Defined on S. So this is the most simplest of the algebraic structure one can think of. Just have a set and a binary operation. There are so many examples: the set of natural numbers, with addition, the set of natural numbers. Once again, it's multiplication of natural numbers, integers is multiplication, and then you can even think of all groups. All groups. Every group is already a semigroup because it is already a set with an associated binary operation, satisfying some more properties. You took a ring, you remember a ring is a set together with two binary operations, multiplication and addition. And then with respect to addition, it's an abelian group. With respect to multiplication, it is a semigroup. That is close and associated. So every ring is also an example of what is a semigroup. So this suggests that the class of all semigroup is much larger than the class of rings and the class of groups, because we have examples of semigroups such as this one, the other one here, and this one, that are not groups in their own right, but they are semigroups. So semigroup is a much richer structure than that of groups and rings. So if you can think of a semigroup as a generalization of these algebraic structures. So there are examples as we are seeing now. But then today what I'm going to do is just to define classes of regular semigroup. So an element in a semigroup, an element A in a semigroup S is called regular if we can find another element X in the semigroup such that AX A is equal to A. This definition is what defines a regular element in the semigroup. So if you have an element in the semigroup for which you can find another element, that AX A is equal to A, this equation is being satisfied, then that element is called regular. For example, if you are in a group, you can always find an element, given any element. For example, if you are in a group, take A, there is always the A inverse that will serve as the X, and then A, if you do the product or you compose of the binary operation, then you get A. This equation is always true in a group. So this is already telling us that every group, the element of every group, when viewed as a semigroup, is always regular. So actually every element in a group is already regular because I can always find the middle element over here. If you multiply A, X, A, you get A. So this is what defines regular element. There are semigroups that are not groups and elements are still regular. For example, if you are working in the full transformation semigroup, like you have, let me take T2 for example. If you take 1, 2 and T3, let's say T3, and then you think of 1 is mapped to 1, 2 mapped to 2, and 3 is mapped to 1, then the map, so this is your A. You can find a middle mapping over here where 2 is mapped to 1 and 1 is mapped to 3, and then you can put 3 over here. This is still an element in the semigroup. That is the set of all transformation. If you do this composition, 3 here, and then you have 2, 1. If you perform the composition, you get what? You see 1, 2 is mapped to, so 1, 2 is mapped to 2, and 2 here is mapping to 1. 2 to 2, so I should have been 2 to 2, and 2 here, so I think I should have picked 2 to 2 over here. So 1, 2 mapping to 2, and 2 is mapping to 2 again, so which means, well, I have to do it over here again. 2 is mapping to 2 again, so therefore I have 2, you can see it, and then 3 is mapped to 1, and 1 is mapped to 3, and 3 to 1 again, so which means this 3 over here is mapped to 1. So you see, you started with A, and you were able to discover an element in the semigroup X, and then with A again, the composite is equal to A. So which means this element is regular in Tn, T2, T3 over here, because this is a set of all transformations on 3 objects. And you know, we see transformation as this. I believe you have seen in one of our videos that this is how we represent transformations. Okay? So element of the full transformation are regular. So, but you know, the full transformation semigroup is not a group, it is just a semigroup, and elements are regular. Just a minute. Okay? Element there are regular. So this is what we call this is what we call regular elements in a semigroup. Okay? So this is what we call regular element in a semigroup. And so this multiplication here, if we perform the product, as we have said, it is to 2 and 3 is mapped to 1. Okay? So, which is still 8 over there. So now a semigroup S is called regular if every element in S is regular. So you can see how we define regular semigroup on the basis on the fact that if every element is regular, that is, the semigroup is called regular in entirety. If every member of the semigroup is regular, because you can have a semigroup where some elements are regular and some elements are not regular. So but if it happened that every element of a given semigroup is regular, then the entire semigroup would now be called regular. Just like the groups, every element of the group is regular. So a group is an example of a regular semigroup. A semigroup is also a regular semigroup with the fact that every element inside is regular. Likewise, the full transformation semigroup, because this construction we did here to find this element X can be done in general with every choice of X or A in the semigroup, so you can always do it. So, and this is what defines a regular semigroup. So it is called regular semigroup if every element is regular. So it so happened that if an element is regular, then it will have the property that it has inverse. Well, let me define inverse first. So so an element A a semigroup S is called, or let me say B of a semigroup S is called an inverse of another element A in the same semigroup. If so, two equations here that ABA is equal to A and BAB is equal to B. So you see here, the first equation is already telling us that A is regular. So an element cannot have inverse unless it is a regular element. So when you look at this definition of inverse, it is also, the second equation is also telling us that B is also regular. So if an element has inverse, then the element and its inverse are both regular elements. So in a semigroup, element with inverses are the regular element, precisely the regular element. If an element is not regular in a semigroup, it can have an inverse. But we will see that here, because if A is regular, then already this equation is satisfied if A is regular. And if one choose, if A is regular, then we can choose what? B to be equal to XA, X. And with this choice of B, we will have these two equations satisfied. But once you choose B to be that for a regular, so what I'm trying to say is that if we pick a regular element arbitrarily from the semigroup, it will turn out to be an element with inverse. Because you can always discover the inverse of a regular element in the semigroup. And this is how we discover it. Because if A is regular, then there is this element existing, so that this equation is satisfied. But then with this element, you can construct a new element in the semigroup, this one, such that with this choice, then you have A, B, A to be equal to, so A, X, A, X, A, but then that would be, this would be A, X, A. So I just rearrange my brackets, from the associativity property of the binary operation in the semigroup. Then this will be, you remember this is A from the equation I just cleaned. So this is AXA, but that is A also. So therefore B is satisfied. The first equation here is satisfied. So this is getting to satisfy the requirement for the inverse. So we have to see that also it satisfies the second equation here. So we now say BAB is equal to.
Sorry.
Yeah.
If that AXA is A, and you have another XA outside, but you got everything to A, how do you do with the other?
We have another XA here.
Yes.
Yeah, you remember you have a bracket like this.
Okay.
But then since the semigroup is associated, you can do away with the brackets.
Okay.
So this is still AXA, and that is A. It's okay, huh? Alright. And also one can see that BAB is the same as XAX, because this is our choice of B, and then AXAX is equal to what? Well, you can perform some associativity regrouping the elements because of the associativity AXA, XAX, but then in bracket here is A. Whenever you have an element sandwich, but this particular element is the element satisfying the requirement of A being regular element. So you have XA, XAX. Is that okay? And then I can still put bracket like this. And then I have XAX, but this is our choice of B. So therefore the second equation over here is also satisfied. So if an element is already regular, you can always discover it is inverse. And well, but the thing is, in a regular semigroup, if A is regular, then I can find X in S such that AXA equal to A. But then the choice of this X, the existence is not unique. So you can have so many elements satisfying this property. Are you following? It's not necessarily that it's only one
Inverse.
element that is satisfying this property.
Okay,
You can have so many of them.
Inverse is
No, this is not inverse.
Okay, and
This is an element
that's
making A to be regular.
regular. Yes.
Are you following?
Yes.
So, but we say there exists an element, but we are not saying the existence is not necessarily unique.
Okay.
I hope it's okay.
Yeah.
This element may not be unique.
Okay.
You can still have another Y.
Okay.
What I'm saying, there can still exist some other Y such that AYA is still equal to A.
Yes.
If it so happen, it means if I choose B still to be equal to Y, AY, I will still achieve inverse.
Yes.
So which means I may end up having more than one inverse in the semigroup.
Okay.
So in a regular semigroup, every element must have inverse, and these inverses are not unique, unlike in group theory. In group theory, inverses are unique. Because in group, if you can still remember, in group, there is one and only one element. If the semigroup is already a group, there is one and only one element that will satisfy this equation.
Yes.
That element is A inverse.
A inverse.
It's the only one that will do that.
Yes.
And so therefore, B equal to A inverse X, no, A inverse AX, A inverse, well, A itself. This will still be A inverse. So that means that element is the only one. Are you following? Because this is actually A inverse.
Yes.
So that inverse is always the only element satisfying this equation.
Yes.
So you cannot have more than one inverses in a group.
Right. Yes.
But in general, regular semigroup, element can have more than one inverse.
Okay.
That is in the event where you have more than one element satisfying this equation. Like here we have Y and X. We assume to have Y and X. And we can now see that if we choose B to be this, we have an inverse. And if you choose B to be this, you have a different inverse.
Okay.
So in a regular semigroup, an element can have so many inverses.
Okay.
So many inverses. So, so for that, if S is a regular semigroup, and A is an element of S, then in the theory we denote by V of A, the set of all inverses. Yeah, the set of all inverses of A in S. So in other words, V of A is equal to the set of all B in S such that ABA is equal to A and BAB is equal to B. So this is the collection of all inverses in S. And it's a subset of S because we are taken from S. So this is clearly a subset of S. It may be the entirety of S, it may be something else. So this is a standard notation in the theory when you are studying regular semigroups. Then you have to see that this is the case. There is actually a result that if you are looking for the inverses for a product of A and B, this would be always contained in the set of all inverses of A and the set of all inverses of B. Okay? Then equality may happen in some instances. So, but this is
when you take the product of two inverses, then it's going to be a set of inverse in A and set of inverse in B.
Yeah, like you are multiplying set here. So meaning you are multiplying element wise. Here is one single element, the product of A and B. Then you are looking for its inverses. You should look for it from inside the set. You don't have to look from the entirety of S. So that's the advantage of this particular observation here. So now we since we said we are defining classes of regular semigroup, because what I noticed is that the paper is talking about classes of regular. Some is mentioning a lot of classes of regular semigroup. So and that is why we have to understand all this. So a regular semigroup now is called a regular semigroup S is called, so number one, inverse semigroup, inverse, so it's an inverse semigroup if the set of, for all A in S, the cardinality of the set of inverses is 1. So this is, every element is having only one inverse, a unique inverse. You understand
for
this?
Inverse,
Yeah.
For inverse semigroup, it's only having one element as a. I don't know. Okay. No.
No, yeah, that is exactly what I'm saying.
Yeah.
Every element has only one inverse, like in group.
Okay.
You know, which means immediately you can now see that a group is an example of an inverse semigroup.
Inverse semigroup.
Yeah,
Yes.
because every element is having one inverse.
Okay.
So if every element is having one inverse in a regular semigroup, then that regular semigroup is an inverse semigroup.
Okay.
We have characterizations of this kind of things. For example, if you can check that the semigroup is regular and the idempotent commute,
Yes.
then you can conclude that it is regular.
Okay.
So a regular semigroup in which idempotent commutes
Okay.
is an inverse semigroup automatically. So they are characterization, but I'm just giving you the definitions here.
Okay.
Yeah. But don't confuse this with the concept of group.
Okay.
Well, a group, in
Have a
group,
unique inverse.
every element is having a unique inverse.
Eh.
But you have other semigroups, regular semigroup, that are not groups, but still inverses are unique,
Okay.
having unique inverses.
Okay.
For example, if you are working in the semigroup of partial maps, if you take n equal to 3, and you are thinking of in, I3,
Okay.
that is one-to-one partial mappings. If I take an element alpha, for example, like I say 1 is mapped to 2 and 3 is mapped to 1, for example, this is a partial map,
Okay.
in the sense that 2 is not mapped to any element.
Okay.
And it is one-to-one in the sense that no two elements mapped different, and mapped to a common point
Okay.
in the semigroup. But you know from here, if you are to think of finding an inverse, say beta, that will satisfy the requirement. You have only one such beta, it is 2 to 1 and 1 to 3.
Okay.
This is the only beta
Yeah.
that will do the job. So that will satisfy the equation alpha equal to alpha, and the beta is equal to beta. See, if you perform the product,
Yes.
the composition, alpha, you still get alpha, and the beta will still give you beta.
Okay.
And this is the only choice of beta throughout the semigroup that will give you this.
Okay.
So in this semigroup, in general, in In, for all n, you have one and only one inverse.
Okay.
Generally, this inverse is unique. That means the inverses are unique.
Right.
So this is a standard example of an inverse semigroup, one that is not a group.
Okay.
But then generally all group also are inverse semigroups.
Okay.
Okay?
Yes.
So this is one class
Okay.
of inverse semigroups. Another class of inverse semigroup is the class of orthodox semigroup.
Okay.
So orthodox semigroups. So this is an inverse semigroup. It's an inverse semigroup. No, not inverse semigroup, sorry.
Regular.
It's a regular semigroup. S, in which VA, for all A, in S, that is the set VA. What is this?
Set
The
of
set of
all-
idempotent. Set of inverses
The inverses.
is a sub-semigroup.
Mm.
Sub-semigroup
I don't know, the first inverse semigroup.
of S.
Okay.
That is the set of inverses of every. No. Sorry. I think I am. The set of all idempotent, in which the set of all idempotent.
Okay.
Wanted to-
Orthodox,
Yeah.
Zero plus semigroup.
I wanted to characterize in terms of the inverses, but
Okay.
what we are saying is the set of all idempotent. Idempotent in that set is denoted by E of S.
Okay.
It's a sub-semigroup.
So, anytime I think of idempotent, I always think maybe it's a unity.
Of us.
So, but you are not taking the set of all idempotents.
Yeah.
How do we generate?
Okay, since I'm mentioning idempotent
Yeah.
for the first time, maybe I will tell you what idempotent are.
Yeah.
Idempotent, the set of idempotent means the set of all elements E in S
Okay.
such that E square is equal to E.
Okay.
So element that when you multiply by with themselves,
Yeah.
you still get the element back.
Okay.
So any element in the semigroup satisfying this property, just like identity element, if
Identity.
you square an identity element group,
Yeah.
you get the identity back.
Yes.
But you remember, you can still remember in group, it's only identity that behaves like this.
Okay.
Yeah.
Yes.
It is only identity element that you can square to still
Right.
get the
Yeah.
element back.
But in semigroup it's different.
So which means there is one and only one idempotent in a group.
Yes.
But in semigroup you have so many idempotent.
Oh.
You can have so many idempotent. Let me not go too far here. Let me just stay within this semigroup here.
Okay.
You can see this semigroup where you are having partial injections.
Yeah.
If you take this map, alpha equal to 1 to 1 and 3 to 3,
Okay.
and square it,
Mm-hmm.
you get 1 1 3 3, 1 1 3 3. But what is this? 1 is mapped to 1 and 1 is mapped to 1. We are doing composition. 3 to 3, 3 to 3.
Okay. That's what we mean by okay.
But you still have another one. You have beta to be 1 2 3, 1 2 3.
Okay.
But then this is even the identity in this. If you square beta here, you still get 1 2, 1 1, 2 2, 3 3, which is still beta.
Okay.
And you see you have so many of them. You can
Okay.
think of so many of them. 1 to 1, 2 to 2.
Okay.
Still another one.
Mm.
You square, you still get 1 1, 2
Okay.
2.
Okay.
So,
All idempotent.
so in a semi-group, you can have so many
Idempotent.
idempotent.
Okay.
Okay? So, and if the set of idempotent is a sub-semigroup
Okay.
in a semigroup, then that semigroup is called orthodox.
Orthodox.
An
All
orthodox
set
semigroup.
of idempotent is called orthodox semigroup. Okay.
Yeah.
Yeah.
Do you understand this?
Oh yes, I'm getting it.
Okay. You know, one other class of semigroup that is mentioned in the paper is the class of rectangular band.
Rectangular.
It's a rectangular band. Rectangular band. So well, I think I should start with a band first,
Okay. Band.
since I have mentioned idempotent.
Okay.
Let me start with a band.
But if I need to start with the definition of band, then later, so this is the classes of inverse semigroup.
Okay. No. I think a band.
Regular semigroup.
Well, rectangular band.
Right.
Before I talk about. So let me define it in terms of inverses.
Okay.
So a rectangular band is a semigroup in which that is a regular semigroup. A regular semigroup S in which for all A in S, the set of inverses is the entire set.
Okay.
So every other element in the semigroup is an inverse
Okay.
for any other element.
The set of
Then it
all
is a
inverse
rectangular
is equals to then it satisfy what we call rectangular.
rectangular band.
Okay.
Every other element in the semigroup is already an inverse for every other element. So that's such a semigroup. Such a semigroup is called rectangular band.
Okay.
Any group with more than one element
Okay.
is not a rectangular one.
Okay.
Yeah, because if you have a group with more than one element, non-trivial group, it's only the trivial group because you have only identity and it is the inverse of itself. So it's a rectangular one. But once it is not trivial and if it is a group with two elements, 1 and A, then no, obviously A square must be the identity in the group. So A square is the identity. So A is the inverse of itself. But identity is not the inverse of A. Because if you multiply A with identity, you don't get A. You don't get the identity. You get A back. Are you following?
Yes.
So it's not a rectangular one. So non-trivial groups are not rectangular ones. But you can have a semigroup where every element is the inverse of every other element. Because you remember we said in a regular semigroup an element can have so many inverses.
Yes.
So if for all elements the set of inverses is everything, the entirety of everything, then you have what is called a rectangular band. Well, a rectangular band can be also characterized by the fact that so if you look at this, it means we are saying from the internal structure, then what we are saying here is that S is rectangular, is a rectangular band, if for all A in S, for all AB in S, if you take any two A, B is always the inverse of it. Take A and B, any two elements you pick, they are inverses of each other. So it means A, B, A is equal to A. If you take any two elements, they will always satisfy this equation. Are you following?
Yes, sir.
Because B is already automatically, you say the inverse of A is everything. And likewise, the inverse of B is everything. So if you pick any two elements in the semigroup, they are inverses of each other. So they always satisfy this equation.
Okay.
Yeah. And then, well, but dually, you can also say BAB equal to B to go with the definition of inverse. But there is no point in saying this because you are making a universal quantification here. You say for all AB, so you can interchange the role of A and B.
Okay.
There is no order in this choice of A and B here. So therefore, you don't need to mention the second equation. It's just a repetition of the first one. So this equation is this. So you can say a rectangular band is a semigroup. It's a semigroup in which this thing is satisfied.
Okay.
But once this is satisfied, it's already telling you that every element is regular.
Okay. Yes.
Yeah, every element is regular. So which means rectangular band are regular semigroups.
Yes.
So this is what a rectangular band is. But then immediately from this, we can see that rectangular bands will be with the property that if you take any element and square it,
Okay.
you get what? Yeah, you get A times K.
Okay.
No, you get the elements will be so what I'm trying to do is to show that every element is an idempotent actually. So if you take any A and look at A square, then that would be A square A. Yeah, okay. I think it's like this. Okay. So A square will be A square, A. But then that is equal to, yeah, because A square is an element, so I can choose this B to be my A square, my A square, and work with it in here. Do you understand what I did? Yeah, as inverse now, I think it should be A square is A square, A square. Let me write it up here. So if you look at A square, it's the same thing as A square, A square. But then that would be what? A, A. I open up the square. But what is this? This is A. Because even if you choose B to be A here, you still get A. Because you say for all A, B. So this is A. And this will still give you A. So the square of every element in a rectangular band is actually the element. So every element of the rectangular band is an idempotent. Are you following?
Yes.
So, and then satisfying also
This with the regular equation.
extra requirement. So, and that is why a rectangular band, that is why the name band. Well, there is a justification as to why it is called rectangular. This is because of the fact that you can define multiplication in the semigroup to do with the edges of the square. So you can think of the semigroup as being a direct product of A, B, and then so that if you have some element A, B here, and then you have A, C.
They say the product of the two at the vertices. Is there any defined?
B, D.
Okay.
And then this will be, well, this is, no, this cannot be S.
A, D.
This
A,
will
D,
be,
C, B.
is this C?
C, B. Why C, B? Amasa, when they said, when you pick it up.
Forming the edges, if this is A, B, this will still be
the other one is C.
B. And this is C what?
C, D.
C, D, ba? Okay. So this is now D. So D. And this will be A. A what?
A, D.
Yeah. C, D. So this is now C.
I know it's repeating.
Yeah.
So is there any other it follows that they say the product of the two will give you the vertices of the product, or when you flip a 2 points A, B, C, B, as a point in the cartesian plane. So it's the product of the two will now give you the vertices. So does it follow any what other I cannot?
They followed what?
Does it follow any defined distance?
Yeah. What I'm.
For you to get the vertex, that is when you take the product of the 2 points in the cartesian.
Yeah, if you say A, B, for example, here,
yes.
and you say, well, this will still be A, and then, no.
The points are A, B, C, D. So they say when you take the product
C, yeah? Okay. So this is still C, ba? C what? D, go? C, D. Okay, good. And then, so we will have over here, so this would be, what would be the coordinate over here? Okay. Well, the coordinate over here would be. I'm just.
The way the vertices are being chosen, so I don't maybe if it has a defined.
No, you imagine you have x and the y axis here.
Okay.
And so this is the x axis and this is the x coordinate over here.
Okay.
So it will remain to be the same x coordinate. So that is why you are having a over here.
Okay.
And then if you think of this coordinate as the y coordinate
Okay.
here, then if you go up here, you are changing the y coordinate, y coordinate. So that is why it is now c.
Okay.
But horizontally it is remaining to be c.
Okay.
And then if you go vertically here, so it will still be on that same y-axis, so it's d over here.
Okay.
And then the y-axis is not changing, so it will be b over here.
Okay.
So this is what I'm saying.
Okay.
And now, so the reason why it is called rectangular band, because it's a semi-group, it can be characterized as a semi-group. It's isomorphic to a semi-group to the direct product of A and B, a semi-group defined in this way, the multiplication, this, if you multiply this with that, you get this point over here. That is AB times DC will give you AC. Okay? And if you multiply DB with AC, you get what? You get DC.
So I meant to understand.
In other words, if you multiply elements along the edges, the diagonal edges of a square, you get this. The other point. If you multiply like this, you also get this. And likewise, if you multiply like this, you get this one. If you multiply the other way around, you get this. So actually, the product is always on the edges of the square, and that is why square or rectangle. We are not saying it must be a square. So it can be a rectangle, you know. So that is why it is called rectangular band. So it's a semi-group isomorphic to such a semi-group defined in this way with this product formula. Are you following? So this is what we have. But then the name band comes from the fact that every element is a band. So the fourth class of the regular semigroup is the band. That is a regular semigroup. A regular semigroup is called a band. If so, a regular semigroup S is called a band if the set of idempotent is the entirety of the semigroup. So that is a band. So it's actually a semigroup of idempotent. Once it is a semigroup of idempotent, you don't have to say regular because every idempotent is also a regular. In fact, I have not mentioned that in regular semigroup, you must have idempotent. Because if S is a regular semigroup, and so any element A is a regular element, so the equation AXA equal to A is satisfied in the semigroup. But then if you take this element E equal to AX and this element F equal to XA, these elements are idempotent automatically because of the regularity condition. Okay? Yeah. So you have E square is equal to AX times AX. So you can see this is A already, so you have AX, which is E. And likewise, F square is equal to XA square, which is XA. But you know this is A from the regularity condition. So you have XA, and that is F. So they are always idempotent in a regular semigroup. Once a semigroup is regular, it must contain idempotent. And if every element happens to be idempotent, then it is a band. A band satisfying this condition, well, the condition that we wrote is what we call a rectangular band. So these are some of the classes of the band, or classes of regular semigroup that we mentioned here.